May 1997. Grandmaster Garry Kasparov, one of the greatest chess minds the world had ever seen, and the chess world champion at that time, was defeated by a computer called Deep Blue. It was a significant milestone not only in the history of chess but also in the history of computing. That day, a bunch of computer engineers, programmers, proved that computers can be taught to play complex games such as chess and even effectively defeat greatest human minds in doing so. Before finding out how computers became so smart in playing strategic games such as chess, first find out how chess has been created in the first place. So chess was originated from an ancient Indian game called Chaturanga in 1400 years ago. This game also had an 8 by 8 square board similar to chess. According to the ancient Indian language Sanskrit, Chatu means four and Anga means armed forces. Therefore, in this game was about four different armed forces in the king's army. In Chaturanga, they had 6 different pieces, such as the king, the minister or the general, and the horse, and the chariot, the elephant, and the soldier. The horse is quite similar to the knight in chess. The chariot is something like the rook. And eventually, the minister or the general became the queen, and the elephant became the bishop in chess. One of the hardest problems in games like chess is its complexity. Humans can play chess using their memory and their extraordinary pattern recognizing ability. But how can we possibly teach this to a computer? Well, in chess, in the beginning, we have something like 20 different positions that can be moved. And those 20 different positions have 20 different replies. And after only 2 moves, we have something like 1000 different possibilities. And after only 4 moves, we have 1 million possibilities. This number keeps increasing exponentially. And at the end, we have something like 10 to the power 120 different possibilities in chess. This number is extremely large, so that it's much larger than the amount of atoms in the observable universe. To make matters worse, in chess, different pieces have different movements. For example, knights can jump like in L shape. Pawns can move forward as well as diagonally, and rooks will move in orthogonal movements. But chess is not the most complex game in the world. For example, the Chinese game called Go has more complexity. It has an estimated complexity of 10 to the power 397 different possibilities. This is extremely large. So Go is even more complex than chess. No computer can ever be able to calculate all of these different possibilities. If a computer has to calculate all these possibilities, then it will have to calculate it for ages, for generations. So then how computers became so smart, so good in playing chess? To make matters worse, in chess, different pieces have different values. But even though they have different distinct values, these values may also be changed with the positions. For example, when a knight at the middle of the board will have more value than a knight and the edge of the board. Same thing applies for a bishop and for a rook or a queen. Same thing applies. With the position, the value may change. Because of that reason, when we are evaluating movements and positions in chess, we have to consider a number of different factors, such as values of individual pieces, value due to strategic positions, such as pin, skewer, fork, and we also may have to consider values due to check opportunities, values due to castling of the king, and pawn structure. So all in all of these things had made chess a difficult subject to analysis. So how does computers become so smart in playing chess? Well, throughout the years of continuous development, computer hardware had developed from relays to integrated circuits, and the number of calculations per second also increased. The amount of calculations that can be performed in a single second was increased throughout the time. Now, a single microprocessor contains billions of transistors, but still it's not enough to calculate all the different possibilities in chess. Therefore, the engineers and programmers came up with algorithms. These specific algorithms or instruction sets teaches the computer to play chess. These algorithms use hardware resources and perform calculations. But chess has 10 to the power 120 different possibilities. If it had to calculate all of these different possibilities, it would be impossible. So algorithms had to be smart. Now let's imagine you are white and it's your turn. So in the beginning, you have a number of different options or moves available for you. And for each of these movements, black or your opponent will also have a number of different movements available. And again, for each of these different replies of your opponent, again white has number of different movements. Again, for any one of those movements, again black has number of different replies, so on and so forth. So this is called a search tree. And logical point of view, white will always prefer the move which maximizes the white's score, whereas black will reply with the possible move that minimizes black's score or that minimizes black's value. So white will try to maximize its value, whereas black will try to minimize that value. The algorithm constructed based on this principle is called Minimax. But the search tree is so large and it contains number of different possibilities. Therefore, it is impossible to calculate the entire search tree. Nevertheless, the position, sometimes some positions are so good for white or black, so that the opponent will definitely not enter into that kind of variations. Therefore, based on that concept, some parts of this search algorithm, search tree, can be eliminated for calculations. So using that technique, we can greatly reduce the complexity of the search tree. So this concept, based on this concept, the programmers developed an algorithm called Minimax alpha beta pruning. Now let's talk about Minimax algorithm. Imagine if you are white. White will try to maximize white's value based on the logic that the opponent, black, tries to minimize white's value. In other words, both white and black will try to play the best possible moves. Here, nodes represents the positions and the corresponding links represents the possible moves. And we have whites to play first. And white has two possible moves according to this figure. But really, white may have 20 different movements. But here, only two movements are indicated just to describe this concept in short. Furthermore, typically, we can decide a predefined search depth value for the search tree. Here, the search depth value is just 3 positions deep. But in reality, this value can be even 20 positions deep. So, the search tree will be terminated when it reaches this search depth value. Here, the search depth value is 3. So at the end, the values for the end nodes should be calculated. The end node values should be calculated according to the principles described before. Here, various factors such as material count, castling, strategic positions, check opportunities, pawn structure, likewise different concepts, different factors, combination of different factors should be used for the calculation of the end nodes or end positions at the end of the search tree. So based on that end node values or end position values, previous position values can be calculated. All of these values are white's values. Here, a positive number means white is winning, whereas a negative number means white is losing. 0 means it's a draw. So this Minimax algorithm is based on the concept that the white is always trying to play the move that maximizes its position's values, whereas black always try to play the move that minimizes the white's positional value. At the beginning, it's white's to play, then it's black's to play, then again it's white to play, and then again it's black's to play. At that position, the search tree ends. Here, if we consider these two possibilities between -2 and +1, white will always choose the move that maximizes its value. Therefore, in this node, it will choose +1 rather than -2. Here in this position, the white will always choose +2 rather than 0. If we consider the previous node again, this is black's position. It's black to move. Black will always play the move that minimizes the white's value. So between +1 and +2, black will always choose the move that led to +1. Similarly, here black will play the move that led to the minus value, the minimum value, which is -3. Again, it's white's to play. White will always choose the move that maximizes its value. So white will play the move that led to +1 rather than -3. So here in the beginning, white has two moves. It will play always the move that maximizes its value. It will choose this link, this movement, rather than that movement. So at the end, here, the value in this position for white is +1. If both black and white will choose best moves. They will play their best possible moves. At the end, after 3 movements, after 3 search depth value, the white will end up with +1 position. That's what this Minimax algorithm tells at the end. So this is just one algorithm. But then we can use this algorithm plus another concept called alpha beta pruning, which is described later in the next video. So thank you very much.